Welcome back to the other half of 7b. So we have this non-overlapping and overlapping. Now, the reason we are using that kind of terminology is because this really lends itself to the idea of Venn diagrams. So when we start talking about or events instead of and events, one or the other could happen, but it's still one event, like one draw or one button out of the bin or one card pull. We're just expanding the possibility of what we could draw. So non-overlapping is if two events have nothing in common. Like heads or tails on a coin. You can't have both heads and tails. Those are two separate sets if I drew a Venn diagram. Overlapping though, now I've got a double count in the center that I might have to account for in my probabilities. Because remember, we have the number of things we want over the total number of things that could happen. So the number of things we want, counting that can get a little tricky when we start having these ors pop up. Okay. So thinking about that with the Venn diagram, let's say we were looking at a die roll and I wanted, there are even numbers or there are numbers greater than 4. All right. So I know even numbers for a die roll only has a certain set. Numbers greater than 4 only has a small set. But the question is there a number in both sets? Now, I know you guys could just tick it out and count how many things there are, but when it starts to get bigger, understanding how the bigger mechanic works is important. So if I had my evens, and let me change color. Sure. No, I want blue. All right, so I know my even numbers on a die are 2, 4, and 6. Now, my numbers greater than 4 on a 6-sided die are just 5 and 6. So looking at those two sets, yep, I do see something in common. So that 6 is what would go in the overlap. And then the 2 and the 4 would be here. And then the 5 would be here. So there are 4 out of 6 things if I want to know the probability of getting an even number or a number greater than 5. It's a little silly on a die because there's only 6 things. That is why we often go to a deck of cards. So deck of card has 52 things, but if I say I want a number card or I want a face card or I want a spade. So I can count how many face cards there are. I know how many spades there are, 13, but there's an overlap of spades that are face cards. So if I was going to count those, I would take out where they both happen because I double counted it. I counted it once for face cards and then I counted it again when I counted the spades. We'll see an example though. All right, suppose you roll a single die. What is the probability of rolling either a 2 or a 3? You know, if I read ahead, we wouldn't have done that example before. So a 2 or a 3. Well, there's a 1 out of 6 chance for the 2, and there's a 1 out of 6 chance for the 3. When you're doing or, this is still one event. Multiple events get multiplied together, but if you're just talking about, I have several possibilities that I want to count for one event, you can take the individual probabilities and add them because they're not always going to be the same. So here we have 1 over 6 plus 1 over 6, which is 2 over 6 or 1/3. So a third of the time we're going to get a 2 or a 3 when we roll a 6-sided die. Well, yeah, that makes sense. 2 out of 6 or 1 out of 3. Now the probability of rolling an even number or a 1. Okay, I know my evens. I had them up here in red, 2, 4, 6. And now instead of my 5, 6, I just have or a 1. The 1 is not an even number, so these are non-overlapping. There's the word I wanted. So the even number, there are 3 out of 6 of those. And of getting a 1, it's only 1 out of 6. So this becomes 4, 6 or 2/3. Okay. Now let's deal with these cards down here. So suppose you have a standard deck of 52 cards and want to know the probability of drawing a queen or a club. Recall that there are 4 queens and 13 clubs. Okay. So when you have overlapping events, what you do, so the probability of A or B is the probability of A plus the probability of B. And then we take out, if there's an overlap, minus the probability of A and B. So that's why we covered the and first, because one of the ways to do the or is to figure out an and then take it out. Now, if you ever have 3 conditions, there is a way to expand this formula. It just looks a little weird because you add all the singles, subtract all the doubles, and then add in the triple. I'm not going to ask you to do that, which is why I'm not going to write that down because it's tedious to write. But here we can use this formula. When you have larger number sets, thinking about it this way can be easier than thinking about like writing them all out to count them. So on this one, this is the probability of a queen or a club. So that is going to be the probability of queen plus the probability of getting a club minus the probability of getting a queen and a club. All right, so since I prefer my upright fractions, I'm going to write these. So there are 4 queens out of 52 cards. There are 13 clubs out of 52 cards. And there just so happens to be 1 queen of clubs. So she has been counted twice, so we're going to subtract 1 of them off, so we're not double counting her. She's not twice as likely to occur. It's just the way the numbers work. So 4 plus 13 is 17, minus 1 is 16. Since they all have the same denominator, may as well do the add subtract before you reduce. So we have 16 over 52, and both of those are divisible by 4. So we end up with the very, like, I like cards. I don't like the way the card numbers look. Like 13, I don't like 13. Just because I don't like the decimal. But let's see what that decimal is. Like 4 is approximately 1/3, so it's somewhere around 1/3, but may as well. Yep, see, 0.3077, so a little bit less than 1/3, actually. All right. Now, a little more peculiar. You select 1 student at random from a room with 8 students. And then they give us the makeup of the students. We've got Texas State philosophy majors, UT philosophy majors, Texas State bio majors, UT bio majors. What is the probability that you will select 2 students who are either a biology major or a Texas State student? So this is going to use the same thing we were just using. Probability 1, probability the other, minus the double count. So of bio or Texas State. So the probability of bio, which is 2 bio, 4 out of the 8. Alrighty then. I'm going to add the probability that a student is from Texas State, smarter student. I think so. UT is too big. You get lost in the sea of students. I prefer small class sizes. So Texas State students, there were also 2 philosophy and 2 bio, so there are 4 as well. And if we stopped here, 4/8 plus 4/8 is 8/8, 1. So this is a certain event. No, it's not. There's 2 UT philosophy majors that don't fit our label. So this is just me reinforcing there is a double count. Because if we don't account for that double count, then we get a result that we know is ridiculous. Probably shouldn't have backmouthed UT on the YouTube video. Oh well. So the students that are bio and Texas State students are these 2 here, the 2 biology. So we're going to subtract those off because we counted them twice. So 4 plus 4 is 8 minus 2 is 6. So we get a probability of 6 out of 8 or 3/4, 75% chance of getting a bio or a Texas State student. Then there's this other phrase, the at least once. So let's talk about what the phrase means. So oftentimes this is a multiple events, like it could be I'm flipping 3 coins. What's the probability that I get at least 1 head? So we could count, well, how many with 1, how many with 2, how many with 3, or if I was doing even more flips, how many with 4, how many with 5? It gets tedious. There's another way to think about it that involves our knots. So there's at least once is A. The opposite, the not of at least once, not at least once is not, none. So our total probability of 1 is the probability of at least once plus the probability of none at all for whatever the event in question is. And what this means is if I get probability of at least once by itself, I subtract the other over to the other side, what I end up with is that the probability of at least once is the same as 1 minus the probability of none at all. Now, the bonus about this is the probability of none at all is usually a lot easier to calculate than figuring out all the at least onces. So you purchase 10 lottery tickets, for which the probability of winning some prize on a single ticket is 1 out of 10. What is the probability that you will have at least, that should be at least, 1 winning ticket among the 10 tickets? So I could figure out the probability of having 1 winner and the other 9 losers, 2 winners and the other 8 losers, 3 winners and the other 7 losers. And it keeps going. It's tedious. Or I can figure out the probability that none of them are winners. And then subtract that from 1. So the probability of no winning tickets. So if there's a 1 out of 10 chance that it's going to win money, there's a 9 out of 10 chance that it's going to lose. So we are going to be multiplying 9/10. We bought 10 tickets 10 times. So I'm going to use my fancy notation here, my caret key. That means 9/10 raised to the 10th power. So let me just write that next to it. That is a ridiculously huge number. I don't want to know the fraction. I have no idea what 9 to the 10th power is, but it's some disgusting number that I don't want to know. And I know 10 to the 10th is going to be a 1 with 10 zeros after it, which is, what is that, 10 billion? I don't want to know what the fraction is. When it's this ugly, you're going with decimals. So let's get back in there and get our decimal. So 0.3487. So 1 out of 10 chance in winning, 9 out of 10 chance in losing on 1. When I multiply that, it gets bigger. Well, no, it gets smaller. 9 out of 10 is 0.9. So my probability of no winning tickets as I increase my numbers goes down, which means my probability of having at least 1 winning ticket is going up from the 1/10. All right, so we calculated that. So the probability of at least 1 winner is 1 minus the ridiculous 9/10 to the 10th power. Now, order of operations should do the exponent before it does the subtraction. But if you want to be extra careful, you can put an extra set to say, do the fraction, do multiply it 10 times, then do 1 minus that result. Because that is what we want, and 0.6513. And if you look at the 0.3487 above, those two add to 1, which they better since I did 1 minus the result we had before. All right, so if I buy 10 tickets, I got about a 65% chance of having at least 1 winner. So I got a 35% chance of having none at all, which is much higher than the 1 out of 10 for 1 ticket being a winner. Now, that being said, there's other things involved in this, like if you're thinking scratchers, because they're printed in giant stacks. So the number of winners in the stack is predetermined. The odds that they offer are the total number we printed as the bottom and the total number of ones that are winners as the top, which includes the break-even ones. But interesting fact, when a new ticket first comes out, there's more winners to generate buzz. Some people actually use that as a money-making strategy. It's crazy. All right. Example 9. You bet you can roll at least 1 6 in 4 rolls of a fair die. So we're going to figure out the probability. What is the probability you will get at least 1 6 in 4 rolls of the fair die? So standard 6-sided die, at least 1 6. I don't want to figure out 1 6 and then 2 6s and then 3 6s and then all 4. No. Let's figure out the probability of no 6s. No 6s on 4 rolls. So no 6 on the first roll is any of the other 5 out of the 6 possible. So that is a 5 out of 6 chance. And it is the same for the other 3 rolls. They're independent. So I'm just going to write to the fourth here. All right. So our probability of at least 1 6 on 4 rolls is 1 minus. We'll put the 2 over 6, close. Caret is shift 6 on the keyboard if you're curious. So there we go. So you got a little over 50% chance of doing it. I hope you didn't bet money because that's break even odds, not win money odds. Or probability, I should say, because those are not odds. Sorry. Colloquial phrase versus mathematical meaning. All right, I'm going to pause this, and then later I will do the 7C videos. Come on. And stop.